You want to sit down? Okay, let's get started. So last week we talked about exceptional control flow, and today we are looking at a particular type of exceptional control flow, which is system call. We talk about this as this is part of the module in process, and it's a deeper discussion of the process. So they are closely tied to how processes work and how processes interact with the underlying operating systems. So system calls, they are basically a way the one running process or one running program, they ask the OS to do some service that the process or the program itself cannot directly do. Such services including create another process, read the file system, talk to the network, communicating with other part of the hardware. So all of those tasks, one application cannot do directly. They have to go through the OS. And the reason we want to, they go through OS to do that is for security and reliability. If that process makes a mistake, we don't want that process to crash the whole system. We want to separate them. We want something called least privilege. We want to give least privilege to an application, so the application doesn't need the rights or permissions to which it doesn't need. So in modern hardware and modern OS, we have many mechanisms to support this kind of a feature. First of all, at the CPU level, the CPU usually defines multiple layers of privileges. And in the CPU, on the CPU we are using x86 CPU, there are 4 different privilege levels. We call them ring 0, ring 1, ring 2, and ring 3. So ring 0 is the most privileged one. That's where we run the kernel, the operating system itself. We can do whatever we want in this part. So this part is very dangerous. You can, if you make a mistake, you may crash the whole program. Then Intel also have rings 1 and ring 2. They were designed to implement device drivers. Then we have ring 3 where our applications run. So when you play video games, when you watch Netflix, your application runs on ring 3. The kernel runs in ring 0. And we're not really using ring 1 and ring 2 in modern OS design. So most of our modern operating systems, we only use either ring 0 or ring 3. There are many reasons for this. Not every CPU provides 4 privilege levels. Most of CPUs only provide 2 or 3 privilege levels. So if you design OS, do you want to design your OS only work for x86 CPUs? You want your OS to be somehow portable, easily ported to different architectures. That's why you do not use all 4 layers for of Intel. So the application running on ring 0, we also call ring 3. We also call them user land applications. They are restricted. So what do we mean by restrict them? First of all, they have limited privileges. There are some instructions we cannot really execute at ring 3 level. There are many systems registers we talked in this class. We talked about the IDTR, the interrupt descriptor table register. That is a register you can only access, you can only manipulate in the kernel level. Then there are some configuration registers, CR3, for example, to store the address of your memory page tables. We will look at that in 2 weeks. So that is also a register you can only access in the kernel mode. So if your instruction is trying to write to or even read to those registers, your system, the CPU will give an exception. You're not allowed to do that. Then different memory can also be configured that it can be accessed by different code. So some of the memory can only be accessed by the kernel code. For example, the kernel memory itself. So regular userland applications were not able to read or write to the kernel memory. Also, you have multiple applications running on your OS and running on your CPU. One process cannot write or read the memory of other process. So that is also achieved at the kernel level by setting up the memory page tables. Also hardware. We don't want the applications to directly access the hardware. And there is also a special hardware, it's called the timer. We took a look last week. So obviously, the benefit of this is reliability, security. We isolate different applications. We isolate applications from the kernel, so they will not interfere with the execution of each other. The downside of this is it's very expensive. It's very slow. That's why there has been a lot of research for different user scenarios where speed is more important than security. For example, in data center, we have hundreds, thousands, or even millions of computers. But those computers are running in a relatively safe environment. They are in data center, and we want them to be run faster. That's why at the research side, we have a lot of research talking about kernel bypassing techniques. Intel has a feature to let the applications to directly access hardware or hardware buffers to make network processing much faster. That's called the DPTK. I don't know if anyone of you heard of that. So there are a lot of research to do that as well. Then how does the CPU actually know which privilege level it is running in? On x86, this is done with something called the CPL, current privilege level. And it is just 2 bits in the code segment descriptor register. We talked about this register before. Historically, this is just a code segment register in like 40 years ago. Now its full name is code segment selector register, okay? Because this one points to something called a selector, which is not just an address. It used to be just an address. Now it points to a very complicated selector. Then in that selector, there are 2 bits called the current privilege level, and that 2 bits indicate what is the privilege level the CPU is running right now. If that one is 0, means we're running at ring 0. If it's 3 or 2 bits 1, 1 in binary, means the CPU is running in the userland. We're not using ring 1 and ring 2. So every time the CPU changes to a new segment selector, for example, when there is an exception, like you make a system call to enter from userland to the kernel, the CPU will check the privilege levels in the descriptor and also in the selector, then update here to reflect what privilege level we are using. So different CPUs obviously have different design. The ARM CPU, the privilege level is not really in this CS register because they don't have this register. In the ARM architecture, they have special system status registers, and there are also several bits to indicate which level we are running at. So if we compare ring 0 and ring 3, privilege level wise, ring 0, we run the kernel. Ring 3, we run userland applications. Kernel has the highest privilege level, and when kernel is running, the CPL in CS has a value of 0. When we run user applications, CPL, those 2 bits in CS, has a value 0, 0 binary. And hardware level, ring 0, we can do anything we want. we can directly access those I/O ports. We can use those in and out instructions. We took a little bit. We look at that in the first class. And ring 3, we do not allow those instructions to be executed. And the ring 0, we can map and modify page tables. We can manipulate special system registers like CR3. And ring 3, usually we only limit one application to access its own memory. You can give applications more privileges to accessing other applications' memory, but that is all managed by the OS. At the kernel level, we can run all kinds of instructions. Several instructions we already looked at, like CLI, clear interrupt, right? That instruction you can only run at kernel level. Also, there are instructions to set up system calls using syscall. Then the ring 3, you can run all those arithmetic, those control flow instructions like AND, move, and also syscall or int. Those instructions, they can help you switch from the userland mode to the kernel mode. Then ring 3, if you want service of the kernel, you want to talk to the kernel, you need the kernel to do something for you, you need to use the int instruction or syscall instruction. So x86, the OS we are looking at, only implemented int. They didn't implement syscall. Linux implemented both. And for the kernel itself, everything is already privileged. Everything is already in the kernel mode. So you only need to make function calls. If you want to call any kernel function, just use the call instruction to do that. So system call is basically the interface OS provides for the processes running on top of it. And the applications run on privilege level, and the system call is the interface for the application to enter the kernel mode. Like I said, there are int and the syscall instructions. So those two instructions, the underlying mechanism is different. Int, we talked about last week. Basically, when you make an int, you run an int instruction, the CPU will look for the interrupt vector table, or in x86, that's the interrupt descriptor table, IDT. Then it will check what parameters the application is giving me, then I decide what to do. Syscall, this instruction will not look for that table. That table is stored in memory, so it's a little bit slow. And syscall will just look at some special registers which OS set up when the OS boots. So syscall is a faster mechanism than int. But int is the traditional historical interface. That's why modern OS still have that interface. Linux still have that. x86 only have that interface. So syscall enters the kernel performs services, and eventually the kernel return to the application. And that return, we do not use the RET instruction. There is a special instruction called IRET instruction to do that. So system calls, actually, when you program in C, right? So you do not directly invoke system calls. You call a C library function like open, read, even fork. Those are C functions. Those are C wrappers of the system call. The system call itself eventually need to use that int or syscall instruction, but you don't do that. You make the function call to the library, and the library eventually will do that. But you can, when you program, you can also do that because your program has a privilege to run that int or syscall instruction. So in our software security class, when we write exploits, we always write assembly code to do int and syscall directly. So next we are going to look at how it works. So there are many different system calls, especially for the first project. You are going to program a shell. A shell is a program that you can type commands and it will run different applications, programs, and it will return the results back to you, right? So to do that, the shell need to make many system calls. There are some you are going to use. You are going to use fork. You are going to use execve, which we took a look at last week. We even look at the xv6 implementation of that. There is exit system call, open a file, close a file, read a file, and write to a file. There are several other system calls you are going to use. So you are not going to program the OS kernel itself, but you are going to use the interface provided by OS. But we are going to look at how OS implements those system calls. So besides those system calls, there are actually hundreds of system calls. Something I haven't mentioned, wait is also a system call you are going to use. So this will make sure the parent process will wait for the child process. So the parent process will not exit. Exit will just a process will kill itself. Also kill is a strange system call name. Right now, this system call is used to send out a message from one process to another process. But originally, it was only sending out a kill message to ask one process to quit. That's why historically we call it kill, but now it can send all kinds of signals from one process to another. So modern OS, we have hundreds of system calls. If you look at the xv6 source code, you can easily add your own system calls there. Even Linux, you can also easily add your own system calls there. So Linux right now have more than 300 system calls. Something else you are familiar with, if you have been doing socket programming, TCP/IP, you are using socket. Socket actually is also a system call. Of course, you are using the C wrapper of that socket, C function, but that eventually makes a system call. And the Windows have 700 system calls. And the Linux and also all Unix-like systems, their system calls are similar, okay? They all have open, read, fork, execve, but Windows has totally different set of system calls. Windows they don't have a fork, execve, to start a new process. They have a system called create process to start a new process. That's a totally different interface. So like I said, most likely you are not going to write assembly to make the system calls. When you write an application, you just call the C library function, which eventually use int or syscall instruction to make system calls. For example, if you want to change the current directory, there is a C library function called change dir, change directory, but that is just a wrapper of a system call change dir, also open, read, all of that, okay? So the system call will change the CPU mode. So when you make a system call, let's say you use int, okay? Use that int 80. In Linux, we use int 80. In xv6, int 64, 80 in hex. When your program has this instruction, int 80, the CPU executes this instruction because it's an int instruction. The CPU will look for the interrupt descriptor table, the IDT. And the table's location is stored at that register, IDTR, which is a register, right? That is set up by the OS OS boots. Then it will look for the 80th entry in that table. From there, it will find a selector. The selector describes what is this operation. The selector will say, oh, this is an operation that can be executed from the user land, okay? And when we execute this operation, we are going to execute this function at a particular address. That's an interrupt handler address. And when we execute this instruction, what is the CPU privilege level we should use? So with all that information, when you do an int 80, the OS can, your CPU can enter from ring 3 to ring 0 and start executing a particular kernel code address. Okay, so the benefit of this is you are not allowed, or any user program is not allowed to call arbitrary kernel function. There are so many kernel functions. Kernel is also developed in C. There are, maybe Linux has millions of lines of code. There are many functions. But as a user-led application, you cannot call arbitrary functions. Those functions are not designed to be called by the usernet, right? You can only call predefined set of functions. So those are the entry point to the kernel. And those are the system calls, like open, read. So if you want to check what kind of system calls your program is making, there is a tool called strace. If you do strace on any program, it tells you what system calls this program is making. On my computer, let's do a quick demo. We do a strace. We just want to run the program ls to list the files in the current directory. So when we do this, it tells me those system calls. There are so many system calls, right? Let's start with the first one. Get rid of this. So the first system call you see here is exe-cve, but it's actually not the very first system call. So I typed strace ls in my terminal. So my terminal program is running. When I type strace ls, what is the program I'm going to run? The program I'm going to run is actually trace, right? The ls is just a command line argument to strace. The strace, the terminal program will first fork itself, which is not showing here. And the fork, in modern Linux systems, the system call is actually called clone. But in the textbook, we still call it a fork. And the Linux follow that. So the C library, you have a fork function. The fork function actually calls the clone system call. The clone system call will make a copy of the calling process, or the fork system call do the same. So basically, the terminal application will make a copy of itself. Then one is called the parent, the original terminal application. Another is a child, the one the terminal process created. Then the child process will replace itself because the child process is cloned from the parent. The child process is still the terminal at this moment. So the first system call the child process will make is exe-cve. It's going to replace itself with a new program. In this case, we're going to replace itself with the ls program, okay? Because we want to monitor the system call of ls. So after that, because the return value is 0, means this is successful. So now we have the ls process running from the ls program. Then the ls program will make so many system calls. And the most of this is happened before the main function. So when you program a very simple program, okay, you will see similar system calls at the beginning. This is done by the C library, done by other libraries before your main function. Okay, so not here, because main function is not even a system call, right? It's a function call, so you do not see main here. So the second system call we see here is called brk, that's brick. That is a program trying to figure out how big it, where is the heap of itself. And it returns an address, that's a heap. Then it's trying to do some architecture protection control or whatever, which is not successful. You can see here, it's in this architecture, it's not successful, but it doesn't matter, okay? We can still keep running. Then there is a system called access. We're trying to find if that file exists, which is a library file and called preload. And we don't have that file, doesn't matter. The program can still run. Then after that, we have the system call called open at, okay? This system call is very similar to the system call open or function call open you are familiar with. This is just another interface, tells you where the file is. So you can consider this as similar as open or same as open. Then it's going to open a file, which is also a library called cache file. And this time it's successful. It opens this file and gives a file descriptor 3, okay? File descriptor 3 here, not 0, not 1, or not 2. Because before that, this process already opened 3 file descriptors. 0, which is standard input, 1 standard output, std in, std out, and std error. That's why when here we open another file, another library, we get a file descriptor 3 here. Then we're trying to find out how big is this library. We use fat system call. This is a file descriptor 3. We get how big it is. Then we are trying to node that library. We use memory map to node that library. We're noding that library to this address. So this library, I'm not exactly sure what is that library, but that is a file on the file system. We open it, we node it into memory, okay? So when you write code before, you open something, you read something, right? So you use open, read. So read is also a system call, but read is used to read something very small. Now, if we want to read something big, in this case, probably several pages, in this case, looks like this looks like 20 or maybe several hundred. This is 1 megabyte. So this is like 150K, at least 150K, right? When you read something like this, which quite big, you just use memory map system call to do that. It will be faster. It will allocate more memory for you. So after that, we already loaded the library from the file system to memory. We don't need that file anymore. That's why we close that file. We close 3 here. We just close that file. So then we keep doing that. We keep doing this by including more libraries here. Here we open another library, which is libsenidux library. And because we closed it, so this 3 file descriptor is available again. So when we open this again, we get a 3 again. Then we are going to this type, we are first reading the header. Then we are going to map this. We are changing the memory permission of that memory, do a lot of mapping, close it. Then here we open another library, and this is an important library. This is a libc library. So this is libc. So all your C functions are mapped into the memory address by this function here, right? So what does ls do? When you type ls, what does it do? Lists the files in the current directory or whatever, right? So eventually we should say system calls to do that, right? So after those system calls to know the libraries or whatever, eventually, so we're still loading libraries, another library. After all those libraries, we should find system call to actually look at what files in the current directory. And we can see here. So this is a system call for that. We are trying to open some directory, and this is dot, which means the current directory. We'll open that. Then we are going to get the directory entries. Then we get 4 entries there. Basically, they are a.out, main.c. Those are the files in the file system. So why I'm only printing out a.out, main.c, but here we say we have 4 entries. What are the other 2 entries? In this directory, there are 4 entries. Yeah, exactly. It's dot and dot dot. Okay, that's why we have 4 entries. So 2 of them are a.out and main. Then we are going to print out a.out and main.c in the terminal, right? So what system call we use to do that? We use the write system call. That's why we have a write here. And we're going to write to the terminal. And the terminal has a file descriptor 1 here because std in, std out, std in has 0, std out has 1, std error has 2, but all of them at the beginning, they are all connected to the terminal. That's why we get a.out there. So if we do not do strace, we just do ls, this is what we get, right? We print out a.out and main.c. Yeah. So you mean here, why do I get it twice? No, I don't really know why. I'm not sure. Yeah, because, for example, there are so many system calls. So I can guess what's the meaning of this system call, right? So D here probably means directory. This probably means entry, right? And this one means file stats. This one means IO control. This is also a very interesting system call. Basically, IO control system call is the one users can design to do whatever they want. Okay, let's say you don't want to add a new system call. You want to use a unified interface to do whatever you want. You just put everything in IO control. For this particular, I'm not sure why we're calling it twice and why the results are different. Yeah, I'm not sure about that. So if you want to know what a particular system call do, you can do just a man in a terminal. It gives you a manual of that, and you are looking for section 2 of it, or you just Google or use large language model nowadays. Okay, so next, let's look at how can we make system calls in assembly. Most likely, you don't need to do that, but let's take a look how to do this. First of all, we're going to do this on Linux system, not x86. And Linux, we use int 8 here in hex to do that. And if you Google online, you can find 2 versions of the system call tables. One is for 32-bit, another is for the 64-bit. And very strange, they have different numbers for that. I don't know why they changed the number. For example, in 32-bit, system call 1 is exit. System call 2 is fork. System call 3 is read, 4 is write. Okay, so that is the system call number. And this system call number is put in the register EAX when you run that int instruction. Which system call you want to make? You need to find the system call number and put that number in the register EAX. Then all other arguments you can put in different registers from EBX, ECX, EBX to those ones. If you have more, you need to use a stack to do this. This is very similar to the C convention. So let's take a look at this 10, 12 instructions, and we can guess what system call it is making and what this piece of binary is doing. The very first instruction, we have exclusive or EAX. So EAX has a value 0. Then we do a push. We're pushing 4 bytes onto the memory, 4 zeros. Then we're pushing a strange value here, okay? 68, 73, 2F2, 2FF. Then we push another 4 bytes here. So basically, by doing those 3 instructions, we are putting 12 bytes onto the stack. And that 12 bytes ends with a 0, right? What ends with a 0? A string ends with a 0, right? So it's most likely this is a string. So if we look at the ASCII table, let's say which one will be high address. This one will be actually high address. So 60E will be what? 60E here will be N, 69 will be I. So I have slides for that anyway. Then after that, after push, the ESP points to that string. We're moving ESP to EBX. They are pushing EAX again. EAX has 0. We're getting another 0 onto the stack. We're pushing EBX. So EBX has the address of that string. So the address of the string is pushed onto the stack again. Then we move. This is Intel. This is Intel syntax. This is not the AT&T syntax you're looking at. So it's actually ESP moved to ECX. It's a reversed order. So we move ESP to ECX again. So then ECX will point to 2 addresses, and those addresses will point to 0. This one points to 0. Then we're going to move B to AL. Then we have this int 80. So this is the system call instruction, int 80. And the system call number is in the register EAX. At the beginning, EAX is 0. Now we're changing B to AL, right? So what is B? B is value 11. Okay. So if we look at our animation, first we get an EAX as 0. Then we push EAX. So we have some zeros here. Then we are going to push those 2 values onto the stack. Then we are going to, so that actually maps to the EXE CVE system call, because the system call number is 11. If we go back to the previous table, here, 32-bit architecture, EXE CVE has a system call number 11. Okay, so that's why we're making this system call, basically replacing existing program to a new program. So this is a C prototype of this system call. The first parameter is the file name, the program name you want to run. Then we have the argv and also environment variables. In this case, we set both as 0. The most important thing here is just the file name. So the file name is actually /bin/sh, which is a shell. And that is this string here. This string is actually /bin/sh. So 64-bit, the system call number is reordered. I'm not sure why they reordered it. Read now have a system call number 0. Write has 1, open 2, and those system call numbers are still stored in the register RAX. The parameters are in RDI, RSI, RDX, R10. So this is similar to the calling conventions of just a regular function calls. You are putting the arguments in those registers. So this is a 64-bit version of a system call EXE CVE. Okay. So first of all, the system call number changed from 11 to 59. Okay. Then you need to put 59 in the register RAX. You need to do, you can do, when put the file names, the name, the address of the file name in register RDI, then argv, RSI, environment variable in RDX. And this is a code to do that. RAX, push RAX, then RDX set as 0, RDX set as 0, RSI set as 0 as well. The arg1 and arg2 we set as 0. And then we are going to move this string to RBX. So this is the string itself, not the address of the string. Then we're going to push this string onto the stack. Now on the stack, we have this string, and the address of the string is in RSP because we just pushed it, right? So now we push RSP again. then we pop RDI. So RDI will have the address of the string in this case, and RDI should have the address of the string. Okay. Then we move 59 EXE to AL. Then instead of use int, we can use system call instruction to do that. Okay. So that's a difference in 32-bit and 64-bit. And on 64-bit, you can also use the int instruction. Okay. System call is much faster. That's a main difference. There are several special system registers specifically designed for this because applications make so many system calls. So Intel decide, actually AMD started this. I think AMD, they introduced, both of them, I guess. They introduced this design, and Intel first have an instruction called sysenter. AMD has an instruction called syscall. The underlying design is similar. Then eventually the AMD's design, syscall, get more popular. So that's why we're using syscall. Even Intel is using this instruction. There are at least, I remember at least two special registers to do that. The idea of that, you can guess, it's similar to the interrupt table. You still need to put the syscall's interrupt handler, which is a function's address, somewhere. And now we're putting that address directly in the registers. We do not put that in a table. Otherwise, you need to look for the tables and the multiple layers of memory lookup. So things will be faster. Actually, I tried to write some code last night to show the benchmark, to show syscall much faster. But there are some errors, so I couldn't finish last night. Okay, so here is another animation to show how this works. We use int80 as example. When your software usernet execute int80, that instruction will push the current program counter, the EIP. It will push the code segment selector and also flags onto the stack. It will actually push that onto the system stack for that process, not really the usernet stack. Then the CPU will transfer the execution to the OS handler. To this end, it will look up the interrupt vector table or interrupt descriptor table. From that table, it knows that I'm going to switch my mode from ring 3 to ring 0. After that, it will execute some kernel code. So all of this part is actually OS code, right? After that, the system call handler, it will first save the process's state. All the registers it will save. It will use the register EAX to locate which system call this is. It will execute that. Eventually, it will restore the process state and put the return value in EAX. So Thursday, we're actually looking at this piece of code. Today, there are more code we're going to look at. Eventually, then we're going to do an iReturn. That's another special instruction, different from the return instruction. And this one will pop EIP, pop CS, and eFlags. So CS, it has a value of what privilege level this piece of program should execute. So when we pop this into the register CS, the CPU automatically switch from ring 0 to ring 3. So basically, start executing in userland again. So we can skip those. There's a different system calls and their argument. Open is another example. Open, it has also use a file name as the first argument, and also what mode you want to open as the third argument. You want to open it as read only, you want to open it to write to it, or you want to truncate it. So from userland point of view, this is very simple. Here, we just move 2 to EAX. Then we just do system call to open that. Before that, we already set up the file names. So this is one type of exceptional control flow, as we talked last week. And this type of exceptional control flow returns to the next instruction. Okay. After syscall, we're going to execute the kernel code. After kernel code, we keep executing compare. Okay. We don't go back to system call and execute. There are some exceptions where we go back to this instruction and execute. Usually faults. And this is a synchronized syscall. So let's take a look at the xv6 code, how xv6 set up the system calls. So first of all, xv6 doesn't use syscall. It could be a good homework to implement that, but not for this class, I guess. So it only uses int, and int will go to that interrupt table, and we actually looked at this piece of code last week. So this function tv init is going to initialize all 256 entries on that interrupt table. However, there is one entry it takes a special care, which is this entry. So first we set those 256, then we set up this syscall entry again. Okay, so this entry, I'm not sure about this number. What is this number? I think it's 64. You can search this. Oh yeah, it's actually here. See, 64. So the entry 64 is used for syscall. Okay, you can obviously choose another number. Just do not choose anything in the front 2032. Those are reserved, right? So Linux use 80 in hex, which is 128. I think. Okay, so here is 64 in decimal, and Windows, I believe it's used 2E. Used to use 2E. I'm not sure now. Especially now we don't necessarily use that table. We just use syscall. Okay, so here you can see we are setting those vectors, and this is also very interesting. It's called DPL user. Okay, we talk about CPL, current privilege level. It indicates the CPU mode or CPU status when you are running this piece of code, current privilege level. And this field is called descriptor privilege level. This field means this piece of code, this interrupt handler, can be triggered by the userland program. Okay. The descriptor privilege level here is user. Means anyone on the system can make the system call. There are many other kernel programs and also other interrupt. They didn't set this. So user applications cannot trigger those interrupt. Okay. When user application try to trigger, let's say int 4 or int 5, the CPU will raise an exception because that descriptor says that the usernet programs cannot do that. Okay. So that is the interrupt table. After looking up in the interrupt table, eventually we are going to look at the register EAX to decide what system call this is. And that is defined in the syscall.c function. So here we have many system calls: change directory, close, duplicate, exe, cve, exit. Okay, so this code coding convention is very similar to Linux. Linux also use sys underscore to code system calls. So those are the internal functions. And they are set up basically in this structure. So this is just a code pointer array. So look at this. We looked at this last week. This is the C syntax. See if you guys still remember what this is. First of all, this is static. Okay, we didn't talk about this. A function can be static, means this function can only be called by functions in this file. Then the identifier here is syscalls, and it is an array. And there is a star. And in this pair of parentheses, which means this is an array of function calls. Okay. And for each array of functions, okay, for each function, they have the same, all the functions, they have the same prototype. They return int, and they do not take any argument. Okay. So actually, all of them, they will take some argument, right? But why it's not showing here? At the C prototype, we're not showing the argument. We just show void. But of course, they will take argument. The rate will take the file name, right? Why is that? So if we have parameters here, where do they go? They go to the stack or registers? They go to the stack, right? Because it's 32-bit. But already set the parameters in the registers. That's why we don't need them anymore. Okay. So in the implementation of this, we will just look at those registers. We will find the parameters. Okay, so next we will talk about piping, redirection, and we go back to several system calls. The reason we are looking at this is because you are going to finish the first project. And the first project is to code a shell. It will be quite challenging, I guess. And there are several concepts we need to study before you code that. Then next week, Thursday, we're going to talk about context switch. So piping and redirection, we actually have been using this. So on Unix-like systems, they are with the shell controls where a program gets its input and also send its output. And you are going to program a shell. That's why you are going to code those features. Redirection basically means sending a program's input or output somewhere else other than the default. Okay. By default, we have std in, we have std out, we have std error. Okay. So those are the default for any Unix-like program. So which means the program is supposed to, by default, to read something from the std in. Usually that's the terminal. And it will output its output to std out. The error messages will go to std error, and all of them will be the terminal, most cases. So you can change that. You can change the std in, not from the terminal, but from a file, from many other places. Or output, you can also change that. Then piping will connect two programs. So the output of the first program will be the input of the second program. And you can pipe many programs together. Then the input of the previous one, the output of previous one will be the input of the next one. So when you type this in the shell, it's actually the shell's job to use system calls to make kernel manipulations to make this happen. And you are going to program a shell. Okay. So std in has a file descriptor 0. When you have a program running, this is already opened by the system. The reason is all the Linux or x86 program, they have a very common ancestor. In Linux, there is a program called init. So that is the first user land program. And that program already have those opened, those 3 file descriptor opened. So any other user land applications was eventually cloned or forked by that init program. Okay. So we have the shell. When you type ls in the shell will clone itself or fork itself, then do an execve, right? Then it becomes ls. So shell opened that 3. So ls also has those 3 opened at the beginning. And the shell comes from many other programs. And eventually its ancestor is the init program, which has those 3 opened. Then std_out has file descriptor 1, std_error has file descriptor 2. So redirection. So this is what we do in the shell. This is the syntax. We can redirect the output. You can use the default output is file descriptor 1, right? So you can write 1 and the greater sign, or you just use that greater sign because output of the default is 1. Okay. So let's say if we do echo h, then we have this sign, then we ASDF. What will happen? So what is the command here? What is the program you are going to run here? What is ASDF? It's actually a file. So echo, so here is not piping, this is redirection. So echo is a built-in program. It's already a program in your Linux system. And echo will just output your input. Your input here is hi, right? So that's just a string. So let's run this on my computer. We do echo hi, and this program will just send back hi, right? So the input in this case is a command line input, or we do not have to do a command line input. We can do stdin. We just do echo. Or we should do this. How do I keep it stay here in Linux? I thought this one will keep it open. Okay, I'm not sure about that. So, or sometimes it changes. It used to have and it works. Okay, so the output will go to the terminal, right? Because the terminal is the standard output in this case. But when we do echo hi ASDF, there will be a local file called ASDF created, and the content will be ASDF, will be hi. Okay. So what happened here? So I'm using Z shell, and you are going to program your own shell. When your shell read this line, what your shell should do? Yeah.
So it will take the output of that echo command, and then it will put it through the buffer to write a file.
Okay.
Yeah.
Okay. So basically, yeah, that's the idea. So when your shell says something like this, your shell will first say, this is the program I'm going to run, which is echo. To run that program, you need to first make a fork system call. Then there will be parent and child. Then the child will make a execve system call to run the echo program. Then, actually before that, you will decide that you are going to output to this file. But this file doesn't exist so far, right? We don't have this file. So your shell needs to read this symbol, then realize we're going to redirect it to this file. Then your shell will create this file. Then the output of the echo program will go to this file instead of go to the original terminal. Okay, so that is what your program need to do. So this is redirecting, and also you can do appending with two greater sign here. So you are not going to overwrite what is already in this file, but appending something there. You can also redirecting arrows by using two. So basically here, there is a file descriptor. We're not using it here because its default is 1. So you can redirecting the arrow messages using two greater. You can also redirect the input. Let's say there is a, I think I have an example somewhere. Yeah. Okay, so I have some numbers in this numbers.txt, and I use cat to show the numbers. Now I'm going to sort this. So sort is a program that can basically sort things, right? Then the input of sort, I don't want to use the std in, don't want to use the terminal to type in. I want to use this file. So then we can just use sort, the less than sign, then just the file name. So when you develop this, so when you develop the shell, what do you need to do? You need to first identify the program you are going to run is a sort. And you see this less than sign, then you know that the input will not be std in. Instead, it will be this file. Then you need to open this file, feed the input of this file to the sort program, right? So when we do this, we're going to sort this, okay, like this. Then pipe. Pipe is the operation to connect the output of the previous program to the next program. So in this case, we have echo hello-world. So this is a string. So without this part, we're going to output hello-world to the terminal because that's the standard output. However, with this pipe, we're going to build a connection between those two programs. The first is echo. The second is word count. We're going to count how many characters are there. Okay. The output of the first command will be hello-world. The input of word count will be the output of the previous one. So we're going to count how many words are there. For example, we can do, we just did a sort, right? So we did a sort, numbers. Okay. Oops, it's a little bit small. So this command. There are numbers in this file. They will be the input to this program. Where will this program output? First of all, it will output to the terminal, right? Because we only redirect the input, we didn't redirect the output. The output will still be the terminal. Now we are going to pipe the output of this one to the second program, which is word count, right? So it will count, oh, there are 76 characters. Or we can count how many lines are there. There are 21 lines. So this is how we can pipe into things. Or we can do an echo, we can do a cat. We can do a cat numbers. Then we do, so this will output the file content to the terminal. Now we are going to pipe it. The output is not going to the terminal anymore. The output will go to the program sort, okay? The input of sort will be the output of this. The sort will print out in the terminal, right? But we don't want it to print out in the terminal. We pipe it again to the word count. How many lines there, right? So it will give us the same result. Okay. So when you develop the shell, you basically need to find those vertical bars, those pipes, and you need to think how I can program that part. And I'm going to show you some example code to do that. Okay, so now we go back to the several system calls which you will need to implement your shell. The first one is the fork system call. In Linux, it's actually the clone, because in your homework, you are actually using Linux. But you can use the fork. The C level is still called fork. OS level, it's actually use clone. Fork is still there, but we're just not using it anymore. So this fork system call will create a new process by duplicating the calling process. The new process is called the child. The old one is the parent. And both processes will continue executing from the point after the fork system call. However, they get different return values. Fork is a system call. It will give back a return value in the register RAX or EAX. There will be two processes now, the parent and the child. They will get different return values. So they can identify, so the program can identify whether I'm in the child or whether I'm in the parent. So the parent will get the child's process ID, which is a positive number, and the child will just get the return value 0. If both the child and the parent will get a positive number, then you still cannot separate which is a child, which is a parent, right? So the child will get 0, the parent will get the child's PID. If the fork is not successful, then there will be no child. Then the parent will get a return value -1 for that. Then the child initially gets a copy of the parent's address space, the same code, the same data, the same stack. It will get all the file descriptors, environment, and also signals. Okay, so look at this piece of code. This is a program. The program will call the C library function fork eventually. That's the fork system call. Linux is actually clone, but whatever. And this one will give us, this one will return a value. We just call it a PID, right? So this PID, after this line, we're going to have two processes, the child and the parent. But this PID, everything for those two processes are the same, except this PID, okay? The parent, the PID will be the child's PID, which is a positive number. The child will get 0. So after this one, this is our code. But after this one, there are two processes. But both processes are keep running this line, okay? The child will check its PID because this is a local variable, right? It's stored here. The child will check the PID. If the PID is 0, it means I am the child process. So it will print out I am the child process, and it will get its own PID using another system called getPID to do that. Because the PID here, it's not really its PID, right? Here is always return 0. The parent, however, the return value of PID will be a positive number. Then you will check if it's greater than 0. If it's greater than 0, it means I'm the parent process. So the child process will execute this line. The parent process will execute this line. The parent process will print out I'm the parent, and my child will be the PID. The PID is just this local variable. So if there are errors, we just print out an error. And after that, both of them will return 0. That's it. Okay. So if we run this program, so this will be fork. So we run this program. This is only one program. When I type this in my terminal, it will create one process. But this process we're clone itself, we're fork itself. So now we have two processes. The parent process print out the child PID is this, and as a child process, we're printing out its own PID. Okay. So those two output, those two lines are actually from two different processes. Okay. So this is fork. We can also do a S trace on this. We talked about S trace already. Let's do a S trace on this. So when I do S trace A dot out, we will only trace A dot out. We will only trace the parent. We're not going to trace the child. So this is the parent, right? We will skip all the library loading part. We will start from here. This is the fork. This is a new fork system call. In this case, it's actually clone. Okay. There is still call, but we're using clone. So now after this one, the clone here, do we see the return value? Oh, the return value is here. Okay, see? The return value, because this is a parent process, the return value is a big number. This is a PID of the child process. Now after that, it will write, I am the parent. Then it's actually also getting a signal from the child, but this part doesn't matter. Okay. If we want to trace both parent and the child, we use F here. Okay. So at the beginning, we only have the parent. Now we have two different processes. In which one is the child? The child is calling get PID. So this is a child. So this one is a child, and this one is the parent. Okay. So this is a child, this is a parent. Okay. Child is printing out I'm child and also get PID. Parent is printing out I'm the parent and showing the PID of the child. Yeah. So this get PID. Even though you think this is a very simple function, it's actually also a system call. Okay, so how many processes will this program create? It's a main function. Main function calls fork 3 times, then print out the PID. So after this, we're going to create many processes. And each of them will keep executing this line. It will print out its own PID. Okay. 4 times. Okay. Any other answers? 6 times. Okay. 8 times. Okay. Yeah. 8 is the correct answer, right? So at this stage, we only have 1. Okay. So after fork, we have 2. Then each of them, each of those two will fork again. We get 4. Each of those 4 will fork again. We get 8, right? So we're actually getting 8 processes here. So this is a program, okay? Exactly the same program, just showing you that I'm not cheating here. Okay, so we run this program, we get 8 processes. One of them is the real parent. Then there are 2 more very important system calls you are going to use. You don't have to use both of them, just choose one to use. I think duplicate 2 is more flexible. So this is the one you are going to use to develop your shell. So those 2 system calls will create a duplicate of an existing file descriptor. Okay, at the beginning, we have 3 file descriptors, 0, 1, 2. You can duplicate them. You can also create a new file descriptor. You open a new file, then there will be a new file descriptor associated with that. You can duplicate those as well. So file is basically everything in Unix-like systems. Everything is a file. We're going to talk about that next week. So the dupe, this one this interface, this system call, the parameter is an old file descriptor. It will create a new file descriptor that refers to the same file. Okay, the file here could be a pipe, could be a socket, and it will return the lowest number, the free file descriptor. Okay, so you do not choose which one to use. It will just give you the lowest number. For example, when the program runs, it already have 0, 1, 2 opened. Now you do an open. The OS will always try to give you the lowest number. So when you do an open a file again, you will have a file descriptor number 3. Okay, that's why when we look at the S-trace result, we always have number 3 there. Okay, the OS try to do that. Then the old one will not be changed. For example, you do a duplicate file descriptor, then you are going to get a new number. The OS will give to you. Another interface is, instead of asking the OS to give you a lowest numbered free file descriptor, you can specify which one to use. For example, the input will be old file descriptor and also the new file descriptor. And the OS will make sure the new file descriptor will be the same as the old one. However, if the new file descriptor is already opened, then it will close it first. So why do we need this? This is very useful for your redirection, right? When you are redirecting something, the default output will be the terminal, right? It will be file descriptor 2, the standard output. And you want to redirect that to some file. So you are going to replace that standard output file descriptor, which is 2, with something else, right? But if you use the first interface, it will not give you a chance to do that unless you explicitly close this part. You can also do that. Then you will need to make 2 system calls. You need to do a close, then you need to do a dupe. So use this one, you can create, you can overwrite the existing file descriptor. Also, there is a wait system call where allow the parent process to wait for the child process. So the parent will not just exit, it will wait there. So this example of the wait system call. The program will first make the fork system call. The child will print out child exiting. Then it will have make the system call exit. The parent, instead, before it print out, it will be wait there. Okay. After it wait, so the parent process will be blocked here basically. Then it print out to the parent. The child is exiting with that code number, and this code number is the number in your main function. In main function, you usually have return 0, right? You can change to some other numbers, and that is the exit number. So this one for sure, this line will be printed out first, because the child will print, because the parent will be blocking here. After the child exit, then the parent will print out a child exited with that code. Okay, so this is the wait system call. Okay, then we have 2 more, let's say 2 more quizzes. And this will be very useful for your assignment anyway. We are going to look at 2 pieces of code and tell me what they are doing. This is the first piece of code. And this is not even a full function. It's just a code snippet here. First, we have a fork. We get a PID. Then we are looking at child process and parent process. This whole thing, the whole block here is the child process. The small thing here is the parent. The parent is just doing wait, and the parent doesn't care what is the return code of the child. It's just a wait here, okay? So this part doesn't matter. So what matters is the child process. The child process will use the open system call to open a file called create. So if that file doesn't exist, we're going to create a new file. And we are going to be, this file will be write only. We're not going to read from the file. We're going to just write. And also, if the file already exists, we're going to truncate it. Basically, we remove everything already there. Okay. So those are the three flags we are giving. And this is the permission. This is Linux permission. Who has access to this file? Not very important here. So we're trying to open the child process. We're trying to open this file. Then, if this open is not successful, we'll just exit. If the open is successful, what are we going to do? We are going to call the system call dupe2. I should remove this line actually. Yeah, anyway, we're going to the input. So the first parameter is the old file descriptor. This one is the new file descriptor, okay? The first argument is the old one. The second one is a new one. So what is this one doing? This is a key here. What is this one doing?
Redirecting std out into FD to write the file instead.
Yes. So basically, this one is, first of all, it will, because this std out is already open, right? It will close std out for the child process. This has nothing to do with the parent process. It will close that. Then it will duplicate FD to this std out. So what is FD? FD is this file, okay? Out.txt. So after that, std out, we're not pointing to the terminal anymore. Std out will point to the out.txt, okay? So now we have two file descriptor. One is 2, this one has number 2. This one most likely have the number 3 here, all right? Both 2 and 3 point to the same place, which is out.txt. And they are not pointing to the terminal. Since we are open 2, then we just close one of them. We just close 3 here because we're not using it. Okay. So after this, parent and the child process will be different, right? Parent std in points to the terminal. Std out also points to the terminal. But the child, in this case, the child is still the parent process. We're not running a new process yet. Okay. But the child std out will point to out.txt. But the std in will still be the terminal, right? Then we use exe save AE to create a new program, ls. Okay. So here we're using a slightly different function, exe CLP, but eventually there is only one system called exe save AE. Exe CLP is just another C wrapper. The difference is how you put the parameters. Some of them are arrays, some of them are, I don't remember. Anyway, so eventually there's the exe save AE system call. So then what does this piece of program do eventually? What is the program we're running? Yes, we're running the ls. So when we do a normal ls, where should be the output? Yes. Exactly. So this piece of code will create a new child process using the program ls. However, the output of ls will not go to the terminal. Instead, it will go to that file. Okay. So when you develop your shell, you need to write something similar to this. Yeah.
I'm confused by what the capital letter std out.
Yeah. So that is basically, so first of all, this is C code, right? That is not something built in, obviously, right? So in C, that int is that if, let's say, this int is a built-in C keyword, right? Means integer. If is also a built-in C keyword. The FD is an identifier. This is not built-in. This equal sign is built-in. This open is not built-in. That's basically a function. So here, when you look at this, first of all, you know this is not built-in. Okay, this is not part of a C programming language. And usually when we're programming C, when we use uppercase, means this is a macro. That's just a convention. So this macro here, actually it's just a number 2. Somewhere in the code, there may be a define std out file number 2. Yeah, that's it. Okay, another example. Very similar. Instead of std out, we are using std in here, and std in somewhere is defined as 1. Okay. So this is actually a very similar thing. So the program we are going to run here. Yes.
Same thing except the input that user puts.
So std in here basically means the terminal. You are going to input. The program is getting input from the terminal. Yeah.
Yeah. The user is gonna give a file number.
The user will not give a file number. The program will need a file descriptor or file number, you call it. Yeah. So in this case, we will have 2 processes. The beginning is a parent, and this is also the child. The child eventually will create the sort process, right? Sort will take input from std in, like this, let's say. So we run sort, right? It's taking input from std in, so I can put a lot of input here. I'm still typing from my terminal. After I'm done, I do Control D. Oops. Should I do Control D? Yeah, Control D. See, so it's taking input from the terminal. That's why we type sort. Then I'm typing many things here, and that's the input. Then it's going to sort each line of this, and it will output to the terminal. That's why here we say the result again, right? But what if we do not want to take input from the terminal? We want to take input from a file. What's the example I use there? Typing. Yeah. So let's say we want to take input from a file, right? And that's what you are going to implement. So how do we implement this? When you see that less than symbol there, you know that we're not inputting from the terminal, we're inputting from the file. Then you need to open that file and redirect that file to the input of this program, right? So that's basically what this piece of program does. You fork first, then you have child and parent. In the child, you don't touch the parent. In the child, you are going to open this new file, and this is read only. You're not going to write to it. Then when you open it, you get a file descriptor of that. You use that file descriptor to overwrite the std in file descriptor. Then you create this sort process. So now sort input will not be the terminal. The sort program's input will be the file. Okay. Make sense? Okay, that's all I have for today. So Thursday, we were talking about context switch. Sure. Yeah.